Mauna Loa is one of the world's most massive volcanoes and a defining feature of Hawaii's Big Island. Mauna Loa rises 13,681 feet, 4,170 meters, above sea level, making it the world's largest active volcano by volume and area covered. When measured from its base on the ocean floor, it actually stands over 30,000 feet tall, taller than Mount Everest. The volcano covers about half of the Big Island's surface area. This shield volcano is built from countless fluid lava flows over hundreds of thousands of years. Mauna Loa has erupted 33 times since 1843, with its most recent eruption occurring in November 2022 after a 38-year quiet period. The eruptions typically produce spectacular lava fountains and flows rather than explosive eruptions, due to the relatively low gas content of its basaltic magma. Mauna Loa hosts the Mauna Loa Observatory, perched at 11,135 feet on its northern slope. This facility has been measuring atmospheric carbon dioxide since 1958, creating the famous Keeling curve that tracks rising CO2 levels globally. The remote location and stable atmospheric conditions make it ideal for monitoring Earth's atmosphere. In native Hawaiian culture, Mauna Loa is considered the physical manifestation of Pele, the volcano goddess. The name, Mauna Loa, means long mountain in Hawaiian, referring to its broad, elongated shape that dominates the island's landscape. The volcano continues to be closely monitored by the Hawaiian Volcano Observatory due to its potential impact on the island's residents and infrastructure when it eventually erupts again. Mauna Loa is part of the Hawaiian Emperor Seamount chain, formed as the Pacific Plate moves northwest over a stationary hotspot in Earth's mantle. The volcano began forming on the ocean floor roughly 700,000 to 1 million years ago and emerged above sea level approximately 400,000 years ago. Its shield volcano structure results from thousands of eruptions of fluid basaltic lava that flows great distances before cooling, creating the characteristic broad, gently sloping profile. The volcano has two primary rift zones where most eruptions occur, the northeast rift zone and the southwest rift zone. These linear zones of weakness extend from the summit caldera called Makuauao'Veo, which is about 3 miles long and 1.5 miles wide. Mauna Loa's eruptions typically begin at the summit caldera and may migrate down one of the rift zones. The 1984 eruption, for example, started at the summit and moved to the northeast rift zone, with lava flows coming within 4 miles of the city of Hilo before stopping. Scientists estimate there's roughly a 25% chance that future northeast rift zone eruptions could threaten Hilo, home to about 45,000 people. The volcano's lava flows have historically reached the ocean, sometimes creating new land. The relatively fluid nature of Hawaiian lava allows it to travel dozens of miles from the source, potentially affecting roads, communities, and infrastructure across large areas of the Big Island. Mauna Loa creates its own weather patterns due to its massive size. The mountain blocks trade winds, creating wet windward slopes and dry leeward areas. This results in diverse climate zones from tropical at sea level to alpine desert near the summit, where temperatures can drop below freezing and snow occasionally falls. The volcano supports unique ecosystems at different elevations, including native Hawaiian forests with koa and ohia trees, and rare alpine plants adapted to the harsh summit conditions. Many of these species are found nowhere else on Earth. The Hawaiian Volcano Observatory continuously monitors Mauna Loa using an extensive network of seismometers, GPS stations, tilt meters, and gas sensors. This monitoring system can detect the subtle ground deformation and increased earthquake activity that typically precede eruptions, providing crucial early warning to residents and authorities. Beyond atmospheric research, Mauna Loa serves as an analog for Martian volcanoes due to its shield volcano structure and basaltic composition, making it valuable for planetary science research. Mauna Loa's recorded eruption history reveals fascinating patterns. The 1950 eruption was particularly dramatic, producing lava fountains reaching 800 feet high and flows that threatened Hilo before stopping just 7 miles from the city. The 1935 eruption prompted one of the first attempts at volcanic intervention when the U.S. Army Air Corps dropped bombs on lava flows to try redirecting them away from Hilo's water supply. The longest recorded eruption lasted from 1872 to 1877, over 4 years of continuous activity. Conversely, some eruptions have been remarkably brief, lasting only hours or days. The 1975 eruption was among the shortest on record, ending within a single day. Beyond Pele worship, Mauna Loa holds deep significance in Hawaiian navigation and astronomy traditions. Ancient Polynesian navigators used the mountain as a landmark during ocean voyages, and its slopes contain numerous archaeological sites including ancient trails, ceremonial platforms, and burial caves. Traditional Hawaiian chants, mele, describe Mauna Loa's moods and activities, treating the volcano as a living entity with emotions and intentions. The concept of aloha aina, love of the land, is deeply connected to respecting volcanic landscapes like Mauna Loa as sacred family members rather than mere geological features. Mauna Loa significantly influences the Big Island's economy through tourism, agriculture, and scientific research. The volcanic soils create ideal conditions for growing Kona coffee on the western slopes, while the unique geological features attract hundreds of thousands of visitors annually to Hawaii Volcanoes National Park. The volcano's presence also affects insurance rates, real estate values, and development patterns across the island. Properties in lava flow hazard zones face restrictions and higher costs, while the constant volcanic threat requires specialized emergency planning and evacuation routes. While Mauna Loa is the world's largest active volcano by volume, it's part of a volcanic family. Its neighbor Kilauea is more frequently active and has been erupting almost continuously since 1983, with some interruptions. Together, these volcanoes have added over 500 acres of new land to the Big Island since the 1980s. Mauna Loa dwarfs most continental volcanoes. Its base covers an area larger than the state of Connecticut, and its mass is roughly 100 times that of Mount Rainier. If placed on the continental United States, Mauna Loa would span from Los Angeles to San Diego. Scientists are particularly concerned about Mauna Loa's potential impact on critical infrastructure. The Saddle Road, which connects the eastern and western sides of the Big Island, crosses between Mauna Loa and Mauna Kea and could be cut by lava flows. The Daniel K. Inouye Highway, formerly Saddle Road, was rerouted and improved partly due to volcanic hazard concerns. Climate change adds another dimension to Mauna Loa's story, as rising sea levels could affect how future lava flows interact with coastal areas, potentially creating new hazards or changing evacuation routes. Mauna Loa's magma originates from a deep mantle plume approximately 1,800 miles below the surface. The volcano's magma chamber system is complex, with multiple interconnected reservoirs at different depths. The primary magma storage occurs 2 to 5 miles beneath the summit, while deeper reservoirs extend down 25 miles or more into the Earth's crust and upper mantle. Geophysical studies reveal that Mauna Loa and Kilauea share some deep magma sources but maintain separate shallow plumbing systems. This connection explains why periods of high activity at one volcano sometimes correspond with quiet periods at the other, a phenomenon volcanologists call stress transfer between the volcanic systems. The volcano's internal structure includes dense cumulate rocks formed by crystal settling in magma chambers, creating a complex layered foundation. These subsurface features influence how magma moves and where eruptions are likely to occur. Mauna Loa's atmospheric monitoring station has revealed crucial connections between volcanic activity and global climate. While the volcano itself doesn't significantly impact global climate through eruptions, unlike explosive volcanoes that inject ash into the stratosphere, it serves as a sentinel for climate change. The CO2 measurements from Mauna Loa have documented seasonal fluctuations caused by northern hemisphere vegetation cycles. CO2 levels drop during summer growing seasons and rise during winter dormancy. This data has been fundamental in understanding how human activities are altering atmospheric composition. Mauna Loa has been a testing ground for volcanic monitoring technologies. Scientists use thermal infrared cameras to detect temperature changes, ground-penetrating radar to study subsurface structures, and satellite interferometry to measure ground deformation with millimeter precision. Recent innovations include gas sensors that can detect changes in volcanic emissions from space, and machine learning algorithms that analyze seismic patterns to predict eruption timing more accurately. The volcano's accessibility and frequent activity make it an ideal natural laboratory for developing monitoring techniques used worldwide. Mauna Loa's underwater slopes are equally impressive, featuring massive landslide deposits from ancient collapses. These underwater avalanches, some larger than entire mountain ranges, occurred when portions of the volcano became unstable and slid into the ocean. The submarine portions host unique deep-sea ecosystems adapted to volcanic conditions. Hydrothermal vents along the underwater rift zones support communities of tubeworms, bacteria, and other organisms that derive energy from volcanic chemicals rather than sunlight. Volcanic deposits preserve a detailed record of human habitation on the Big Island. Lava flows have entombed ancient Hawaiian settlements, creating archaeological time capsules. These sites provide insights into how native Hawaiians adapted to living with active volcanism over centuries. The volcano's rocks also contain evidence of past climate conditions through trapped gas bubbles and mineral compositions, helping scientists understand how Pacific climate patterns have changed over hundreds of thousands of years. Mauna Loa serves as a focal point for international volcanic research. Scientists from around the world study its eruptions to understand volcanic processes relevant to similar volcanoes globally. The International Association of Volcanology and Chemistry of the Earth's interior regularly uses Mauna Loa data for comparative studies. Space agencies including NASA use Mauna Loa as an analog for volcanic features on Mars and Venus. The volcano's shield structure and basaltic composition closely resemble Olympus Mons on Mars, making it valuable for understanding extraterrestrial volcanic processes. Emerging research focuses on understanding how Mauna Loa might behave as it ages and migrates away from the hotspot. Scientists are investigating whether the volcano will eventually enter a more explosive phase as it moves into deeper water and cooler crustal conditions. Advanced computer modeling now attempts to predict not just when eruptions might occur, but their likely duration, intensity, and flow paths. These models incorporate real-time monitoring data with geological knowledge to provide increasingly sophisticated hazard assessments for emergency planning. Thanks for watching. Like and subscribe, and don't forget to explore more geological wonders on our channel.